I'm an assistant professor at Auburn University. So this talk, I'll be talking about our work in event understanding from multimodal data with neurosymbolic reasoning. So a lot of this work is what I'm going to talk about now is from my advice, work with my advisor, mentors, and students who are listed here, right? So yeah, I guess I can skip this. This is basically what Dr. Sonaria said about me. So my research is basically three thrust areas. So one is event understanding, which is understanding and describing events from multimodal data. So when we say multimodal data, we are talking about videos, audio, images, video plus text, anything like that. Right? And that's been my major research area. And then active vision is a second research area that we are getting into, where instead of having a static camera, imagine a robot or a camera that can move around, can keep looking at different objects in case if there's occlusion and things like that. Then third is sort of AI for medicine and biology, where we are looking with veterinary medicine and agriculture to improve diagnostics and other activities. So the focus of this talk is event understanding, where we are looking at the next frontier of computer vision. So this follows from psychology and human vision on saying that events are central to human experience. So let's say you have a video like what's playing here now, right? So you when I ask you what's going on here, you are most likely to say that okay, this is happening at a location at a given time that has an ending and a beginning, right? And you usually describe it by saying who is performing an action, what action or activity they are doing it, why they are doing this, and how, where, and when. Right. So if you are to describe this video, you'll say that the who is this person, right? He's the main part of the scene, and what is he's playing the guitar or music. Why? Because he's either performing or he likes music, right? And then how is he's learned music and he's playing with his hands. Where is in a street or outside a cafe. When is some time during the day, right? So you build up this sort of representation of this event and say okay, and describe it in terms of these sort of six categories. uh, and the key thing with computer vision that we are looking at is how can you learn to describe this event from this observations that we have, right? So the major mode of sort of learning these semantics is supervised learning, right? So where this is what we traditionally do. So you have some training examples during training that have a sample plus a label associated with it, right? You train some model, right? Any deep learning model will do 3D CNN transformers and so on. And then you during inference time you get these examples and you predict the labels. Now the key thing is that whatever labels that you train with is what you assume will come in the test set, right? Or your inference. So if you train on 10 examples or 10 labels, you expect 10 labels to be in the same 10 labels to be during test set, and then you do it, right? And then the next sort of thing is to loosen this requirement and saying that during training, I'm going to have samples that I'm seeing along with the labels, but also say that there can exist other labels other than what I'm training on, right? So you see and know that this video corresponds to take tomato and this video corresponds to cut tomato, but you also know that the actions take pepper and cut pepper exist. And during inference, you only get examples from these unseen labels, and your goal is to correctly predict these labels, right? Even without having seen them, right? And then you sort of extend that even further, right? And say generalized zero shot, and say same thing, right? So you have some training samples and labels, you have some known labels, and then you have unseen labels. But during inference, you get examples from both seen and unseen labels, so that you have to identify what you've already seen, but also correctly identify something new that you haven't seen. The key thing that you have to understand with zero shot and generalized zero shot is that the labels that can exist during inference time, right? But you don't necessarily see them. But with open world learning, what we are moving towards is you only know what objects can exist and you only know what actions can be performed, but you don't necessarily know the labels. Like take tomato, you know that the tomato exists in a kitchen, right? Or an onion exists in the kitchen. and you can perform some actions like take onion, take tomato, cut, pour, and wash, and so on. But you have not seen these labels before, right? So taking a tomato, you have not seen that action before. So imagine a robot being trained, right? That to act in different kitchens, like we have different actions in an Indian kitchen, different actions in a American kitchen, a Chinese kitchen, and so on. So the goal is to identify what is being performed in the scene without looking at every possible combination that's there. Right? That's what we call open world learning, and that's sort of what we are working towards as the next frontier in computer vision. And so that leads us to the next question, right? So we know how semantics are expressed, but how can we learn these? We know how can we learn them, and how can we infer them? So we talk about different types of inference and reasoning, right? So first is inductive, deductive, and abductive reasoning. Inductive is that the search space, and you generalize existing ideas to form one of it. So if you have a new example come in, you map it to one of the known concepts. So that's supervised learning, right? So that is sort of analogous to inductive learning. And then zero shot learning can be analogous to deductive learning, right? Where a search space exists, and then you narrow down these existing choices to one which you may or may not have seen based on some heuristic. And then open world learning, which is what we'll be looking at in this sort of talk, is you don't know the search space. So you have to create a search space, you have to generate new ideas, and then you have to verify which of these ideas makes most sense given your data, right? So that's sort of like how we do. So if you go to a doctor, right, and ask them, you give all this list of ailments, and then they say, okay, given these symptoms, this is what you could be, and then they send you for a bunch of tests, and then you come back, and then they say, okay, you're diagnosing with this disease, and so on. So that's sort of what abductive reasoning can be analogous to, and that's sort of what we are trying to come up with, a computational approach with deep learning and beyond deep learning that can sort of do this sort of learning in an open world, right? So in open world learning, we sort of say that when you want to do this learning in an open world, you need to have three different criteria, right? One is you need to know what is happening in the scene. That's the source of semantics. Second is the underlying representation, right? So you should be able to express different concepts, as and when you see them. You can have different sort of labels and so on. And then third is, to learn, to continuously learn and adapt. Right? You don't necessarily stick with what you've learned. So you don't necessarily have a train and test phase, but you are continuously learning and adapting to the new scenario. So that's what we as humans do, and that's what the goal of open world learning is. Right? So instead of just saying that given this video, we just say there's a person playing a guitar, rather we want to say that a person's playing a guitar because music is related playing, and then music happens because we have an instrument, and the instrument in this case is a guitar, right? And we'll be able to localize them in time and space and generate these sort of interpretations, right? And that helps us generalize to new concepts and so on. Now, deep learning alone is not quite as suitable for open world learning. Of course, there are different ways of approaching this. And our approach is neurosymbolic learning, where we have deep learning, right? That gives us continuous valued vectors, and then we get from these vectors into some concepts that gives us a symbolic module, and then from there we can have graph-based reasoning, and that can be targeted for different applications because it's inherently explainable. So in this sort of event representation, we take the idea that the who, what, why, and how deals with semantics. So we are going to use symbolic reasoning at these parts, and then the where and when is more about perception, right? So that is where we'll get deep learning, pure deep learning approaches. So when you combine both of them together, then we'll have a neurosymbolic approach that can describe events in all six categories, and that helps us build a more interactive sort of AI system. Right? So our sort of symbolic reasoning is like I said, there can be many approaches. Our approaches is to use general pattern theory, which is introduced by Professor Grenander, who's on the right. He was at Brown University. He introduced this sort of algebraic formulation that allows us to reason over multiple things. And I'll just give a brief background about that, just so you understand what's going on. So here, our use case is that, we're going to use something called ConceptNet. That's a knowledge base that has graphs like what you see here on the right. It has multiple languages, although not a lot of Indic languages. It's more of Latin-based languages are represented in that. And it basically covers a lot of majority of the words that we can find in Latin-based languages, and allows us to have these sort of links between concepts that we don't necessarily have to learn. Like, for example, if you are looking at the concept egg, right? We know that egg is food because, you can have these links like saying is there relationships, or eggs can be used for food, or eggs can be found at a plate, and so on. So it allows us to encode common sense knowledge that humans take for granted. But here it's a sort of a symbolic representation of all basic concepts that we have in English and many languages. Right? So with pattern theory, what we have is a combinatorial problem, right? We basically say that complex structures, like when we say who, what, where, why, when, and how, these are complex structures that can be built from very simple ones by saying that, we have each of these things are concepts or symbols that can interact with each other to form bigger combinations. And these interactions can be constrained locally and globally. And then we can have some probabilistic, constraints on them to express variations, right? And the nice thing about pattern theory is that it's a unified network of, or a framework for all sort of probabilistic graphical models, and it's a very nice sort of framework that's there. And there are 4 components to it, right? So one is generators, which are these basic symbols. Then you have similarity groups that allows you to apply equivalences among symbols. So for example, if you're looking at egg, which is a food, we can also say that if you don't see an egg, a banana is also food, right? And if you say banana, you can have another symbol, similarity group saying that apples are also fruits and within the same class, and you can perform the same sort of actions on these symbols. Right? So that's what the similarity group refers to. And then we can say have a local regularity to say, how these symbols interact with each other. And then we can say a overall constraint on the structure, saying this is the global regularity, right? And then we can define a probability space over these structures. And, for example, given these video here, we can detect these symbols here, like, stir, the action pick up, the objects spoon, dough, and bowl. And then you can come up with sort of a structure that combines all of them together, that expresses the sentence that you are picking up a bowl with dough while you're stirring the dough in a bowl using a spoon. Right? So this is what we call a configuration, and this forms the basis for open world learning, where we can detect and represent sort of concepts with the graph structure. So this graph structure is a connection graph, and this sort of is how probabilistic models can be expressed with pattern theory, right? So the key thing to remember here is that, all the other graphical models have a fixed structure, right? So if you have undirected pre-specified bonds with a lattice connection, you have an MRF, Markov random field. If it's directed and DAG connection, you have a Bayesian network, and so on. So we, sort of let this structure to be variable and reason over the structure, and it allows us to be more flexible. So now that the background stuff is out, so we can talk about our actual system, right? This is a first version of our system that we built from 2018 till 2019, I think. This was during my PhD, where we first showed open world learning with a slightly open world, right? So this is sort of the stack that we proposed, where you have a deep learning feature stack, right? That takes in frames of videos that comes in, and then along with bounding boxes, it detects objects and produces some labels. So for example, it will detect all the objects in the scene and then come up with a list of labels that are associated with these objects and some actions that can be performed on these, right? And then from there, we get into symbolic reasoning, where we take each of these concepts and then derive what they mean, right, based on concept net. So for example, when we say egg is detected, we say, egg is a food, and then we come up with these sort of links that allow us to connect with each others and build a complex structure like what we have. We call this an event model. So this is a graph-based representation that has embeddings or continuous values for each node, as well as to the edges, so that allows us to reason over what we see and what we perceive. Right? So this is sort of the overall framework, right? So we can do multimodal stuff because we can independently process excuse me, video and audio for object recognition and action recognition, right, with sound analysis and regular CNN based models that we have. And then for every object that we detect or every action that we recognize, we don't just take the top one action, right, which is what we traditionally do, but we say that, okay, we take the top 5 or top 10 actions and top 10 objects, right, and say, okay, because we want to say, with some degree of confidence, right, so if you have any occlusions or any such thing happening, right, you should be able to account for any uncertainty, right? So we take these sort of labels for actions and objects, and then we come up with an inference engine that has an energy based mechanism that uses concept net to generate these overall interpretations that we have here. So to sort of summarize very quickly without going too much into the math behind this, the idea was to say that, given this configuration that we have here, we say that, it's two things, right? So one is that how much support does this object or action have directly in the video or audio, right? And then how much does this action object combination have support in prior work, right? So in terms of concept net and other videos that we've seen. So this allows us to, generate hypotheses and then check whether this makes sense or not, right? And this we formulated in terms of an energy based function where, we take the feature level energy, and then we look at how good these are related and how well the background concepts support them, right? And we reason over this structure, right, using a simulated annealing approach using an MCMC, Markov and Monte Carlo process that allows us to generate a configuration, try different combinations, and then figure out whether the combination that we are trying works or not. So to be more colloquial, you basically check out the combinations of each of these objects with each of these actions and say which of them makes sense, right? So you can cut with a knife, but you'd have a very hard time you know like scooping with a knife, right? Or eating with a knife. That's harder, right? So we look at these combinations and then we say which of them has the best sort of um, probability of occurring based on our energy function that we defined, right? And so what we did was we didn't just have simple connections like put plate on egg, which is what you'd expect from like captioning, video captioning, or just label recognition, right? But rather, we want to come up, like I said, with a better sort of representation that allows us to expand our concepts, right? So this is my sort of my favorite example to show out of my PhD that we had, where the term spray is not even part of our detected vocabulary, but given this video, based on the audio and the video features that we had, we were able to come up with this sort of graph that explains this uh, video that says, you're spraying something on a pan, and then butter was not even detected in the scene. We don't need, so our algorithm doesn't know what butter is, right? But because we are looking at concept net and common sense knowledge, we are saying that if you're in a kitchen and you're spraying something on a pan, right, it's most likely butter. And when we sort of look at other interpretations of the scene, we see that the other alternatives were like spray oil on butter or spray paint on butter and so on. So, or spray oil on a pan and spray paint on a pan and so on. So so the idea was that we are able to generate these interpretations of things we have not seen before, and it makes sense, right? So that's what we call the slightly open world, because we are trying to detect things that we know exists and we can recognize it individually, but not in a compositional way, right? And then our V2, right, which was more recent, and then we have another work that's under review right now, where we are moving completely towards an open world, right? So where we are just using prior knowledge to generate and evaluate concepts, right? So here, the problem is that we don't know what exists. We only say that we know these objects exist. We just know these actions exist, and we don't know where these objects are. We just have this video that are there. So we have this thing called a packaging problem, right? Where they're given a scene and all the objects, what is being used, right? How can we, choose these objects that are, participating in a current action, right? And of course, you don't have this domain correspondence that we had with the other open world stuff and so on. So this is this is sort of our a framework where we extended the prior work. The first thing that we did was to use attention as a driver of perception. So what you see here is our mechanism to predict where a person is looking based on their actions. Right? So this is an egocentric video where people are wearing cameras from on that's like on their eyes or from where they're looking, and the sort of heat map that you see is our predictions of where the person is looking, and the little squares that you see here are where the person is actually looking. So we had some discussions with people from psychology and said, okay, where you're looking is most likely what you're doing, right, or what object you're interacting with, and we say we're going to use that to figure out where your what objects you are looking at. And we said, okay, we're going to ground these objects in an initial vocabulary. Assume that you can detect 40 objects initially, and then you're going to learn more objects from these 40 objects, right? And then from these 40 objects you're going to learn actions, right, from there. So we again use an energy-based mechanism that allows us to filter region proposals from object detection models, and then we use where you're looking at and what's the closest object to it that we detected, and then we constructed our generator space, which is what we reason with, right? So the idea is that we know these 40 objects that we can recognize with a high degree of confidence. So whatever new objects that we see must be related to this object somehow, because if we are detecting an object, it must look visually similar to the object that we already know, right? So this is sort of an example for that, right? So let's say that, so in our example, our object detector only had a frisbee that it had seen, and it had never seen a plate before, right? So when we did inference on kitchen videos, it detected all plates as frisbees, right? So that means that visually these two concepts look similar. So that means that that's why our object detector made this initial sort of correspondence. So now we can establish correspondence across domains, right? So frisbee is not really in a kitchen domain. A plate is not necessarily in a sports domain. So we can sort of establish links across domains by not just saying they're related to each other, but rather compositionally. So when we mean by compositionally, we say that a frisbee, we look at the different properties of a frisbee, like it's round or it's a circle, and it has the property that it's flat, it's throwable and so on. And then we look at the target variable and say, okay, a plate, what properties does it have, right? And do they have any shared properties that are visually popping up? And that sort of gives us a reasoning space to given some energy function, we can come up with a probability of looking at new objects given our old object, right? So for example, if we detected an apple, we look at the compositions, like saying it's a food, it can be found in the kitchen and so on, and we can generate these labels saying that it might be a tomato, or it might be a lettuce, or it might be bread, right? Or if you detect a book in your kitchen, you're most likely looking at a recipe, or it might be an oven or some sort of container and so on. And if you see a bottle, you're likely to having milk in there, or oil, or honey and so on, so depending on what you're looking for. So we can generate new concepts, and so these are our hypotheses, right? So we say, okay, these might be the things that we are looking for, right? Because we see other objects in the scene. And then we use ConceptNet, and in our recent works we use ChatGPT, saying that we just ask what are some actions that you can perform with this object jam or a napkin or a bowl, and we can generate these actions, saying that you can put jam or spread jam, or you can cut something with it, or you can put a napkin, fold a napkin, clean a napkin, and so on. So we can generate what sort of actions can be performed with these objects, right? And then once we have this, we can just use our simulated annealing, and we can generate sort of new configurations and the interpretations of what's happening in the scene. So this is a lot of numbers, but the key thing here is that our approach is getting 21% on this data set, while if you're just training fully supervised on that data set, you'll get 45%. So without knowing what we are looking for, we can get half the performance of a fully supervised model, right? So we are learning new concepts without training. So if you look at these fully supervised models, they've been trained on thousands of examples, right? And these are labeled, and it's very expensive to collect these data. But we don't need anything else. We just use our own, common sense knowledge, so we can label these data with a high degree of accuracy, right? Or for what you can expect with, not knowing what it looks like. This is for action. So verbs, we don't even know what the verbs or actions look like. We don't know motion parameters. Just given the object label, we are able to generate, what are these actions that can be performed on them, right? And it's just doing really well compared to objects, and shows how well you can estimate what a person can do with just knowing what object they're using, right? And this is sort of one of my favorite results from this work, where we say that if you don't even know what objects are being or what actions are being used, we can still just, considering all actions in the English language, we can detect the action with 83.7% accuracy in the top 25 labels that we generate. So that's pretty cool, right? So because we don't really know what we are looking for, we've never seen an action before, and just given a video and what object it is, we can figure out what action you're performing on it. So that means that gives us hope that if you put a robot in a new environment, it can adapt quickly to that sort of environment without taking it out and training all over again and presenting it. So any questions with that? Sorry, I might have gone pretty fast with that, but yeah. So we extended it into text as well. So where given the same thing, right? So if you have unlabeled data and some common sense knowledge base, we can generate these interpretations from directly from text, and then use that to answer questions, right? So for example, if you have the text that's saying that on stage a woman takes a seat at the piano, and then and then blank, and you want to complete what happens next, right? So and you give two possibilities, we can come up with the same idea with abductive reasoning to generate these interpretations, and then infer which is better, right? And that basically shows that instead of just looking at videos, if we look at text, we can outperform zero shot capabilities of models. This was before GPT-3 came out. I think when we submitted, that's when GPT-3 came out, and we compared with GPT-2. And by the time this was accepted, ChatGPT came out, right? So everything just went haywire after that. But the idea is that we can come up with different sort of tests for this approach. It can do visual reasoning, it can do text common sense reasoning, you can do semantic similarity, text classification, sentiment classification, and it outperforms everything that was before GPT-3, right? And the cool thing was that it was very explainable in nature. So the idea was, if you just gave this text a scale as necessary to determine BMI, our approach came up with this graph that said, okay, BMI is body mass index, and it is used to measure stuff, and then measure means you need a scale, right, and so on. So you come up with this sort of graph that explains why the model made the decision to complete this text with BMI as opposed to any other word. So with neural networks, you don't necessarily have access to its internal mechanisms, but with neurosymbolic work, we know exactly why it made this decision. And with this work, we actually went back and trained Bert and Roberta and all these things, and it performed better than just training Bert from supervised data. So that's one part of event understanding. The second part of event understanding is pure deep learning, which is what something that we've been doing in the last 3-4 years. Because of course, students and the people are more interested in deep learning part, or the pure deep learning part, right? So that's where the second part comes in, where and when things happen, right? So like Dr. Sanoria said, when this started, my training was in computer science, but I was also advised by a cognitive science faculty, a psychology faculty. So I also, get inspired from how humans process things in the visual cortex. So based on that, there's a lot of evidence in the brain from the neuroscience and cognitive science community saying that there's predictions happening in our visual system at multiple time scales, and that leads to scenarios where we can figure out when and where actions are happening without having to train for them explicitly. So that's the idea behind our some of our deep learning work, right? So one is when you have so the general theme is that given an input video, right, you do feature extraction, you abstract it to higher level features, and then you predict the features at the next time step, and then you compare you know how you predict versus what it actually turns out to be, and then sort of the difference between that gives rise to different properties in the computational framework. So one of it is segmentation. So where does one action stop and where does one action start? So this work was in 2019, one of our first works. So what you see in the bottom is our list of predictions, errors in the predictions at the frame level. And the blue star is our predictions of where one action stops and where one starts. And the red is the ground truth, where it actually starts and stops. So you can see that, just looking at predictions of how things change over time and how this person is going to react in the next frame, we can detect what action they are doing with a high degree of confidence, right? And if you extend it to spatial recognition, we can localize objects in space as well. So we can generate bounding boxes of where the person is moving or what they're doing and when and where they're performing some action. So the green sort of boxes that you see are hypotheses of where objects can be, and then the blue square that you see is our model's attention maps that we get from predictions, and the blue bounding box is our actual final prediction, and the red bounding box is our the ground truth. So as you can see, if with single actors, it can localize the action very well, because there is not much happening behind, and we don't necessarily detect the person, right? It's just whatever's happening, we can detect it. And the nice thing about this framework is that it can also use to localize multiple objects. So if you have a group of people standing together or playing soccer or playing volleyball, we can detect all of them that are participating in this scene, right, in that particular action. And we don't necessarily have to train for multiple actions as well. It's an emerging property because we can predict at different time scales. So one of the students that joined Dr. Sharka's lab after I left has extended this into animal behavior for wildlife monitoring, and he's been able to do a lot of other work. While my students have uh, been able to connect this sort of framework into a robotic arm that basically, on the left is a simulation of the robot following people around just by looking at what's happening in the scene and just following their attention. And on the right is our robot, an actual robot arm that we built, that watched a movie for almost 3 hours, and then it was moving across the screen, looking at what's happening, and then building event representations to figure out when and where actions happened and who came in and who went out of the scene, and so on. So it built a nice event representation that we can use to summarize what happened, that the robot saw over time. So in our future work, again, this is not just us, but more as a community in the computer vision field. We are moving beyond, trimmed videos, right? So we don't necessarily say that, okay, we have a video that has only this action with only one person, right? So we just have general videos that, many people are working there. You look at the videos and then you figure out when and where things are happening. We come up with these 6 things that describe the scene and so on. And then, moving beyond, egocentric videos for open world learning, right? Can you deal with multiple cameras looking at the same scene? And then, not just recognizing actions, but can we recognize the intent or goal of a person? And then, learning this continuously in an open set manner, and then combining this with robots to build, reinforcement learning based agents and planning based agents that can function in an open world without having just a fixed structure there. So the whole thing is about, not being constrained to what we see in our training data. We say that, the world is a training data. You just have to keep exploring your the concepts that can be present, and then just keep expanding your concepts as and when you see them, right? And not just be constrained to some set of actions and stuff. So yeah, so we've been fortunate to be funded by some of these agencies that have funded myself, my students, and others, and so on. So yeah, I'll be happy to answer any questions you might have.
Thank you very much, sir, for your wonderful sessions. So your talk was very informative. So I hope the audience would have got more knowledge about like practical application, how practically you have addressed the real time problems. And I am so means I have seen like the zero shot learning algorithm is without having the label information of some particular domain. And now still like with the prior information of other domain knowledge, you can still recognize or still you can address the problem, right? So that was very interesting talk, interesting knowledge for the audience. So participants, if you have any questions, so it is open to you. So you may ask questions. Imam,
Thank you, Sathyanarayanan.
Yes, ma'am.
Can you just go back to the slide that you're presenting about the natural language inference?
Yes, ma'am.
Yeah. Yeah.
This,
Can you just shed some light on how you would use this knowledge graph along with that?
yes. So what we did was, so instead of just training, say that you have a question and then 4 answer choices, and then you train Bert to pick one of these 4 choices, right? So that usually have access to the ground truth about which action is correct, which answer choice is correct. So what we did was, given this sort of sentence, right, your question and your answers, we can come up with a graph based on ConceptNet that again has an MCMC based reasoning mechanism that allows you to build this graph from ConceptNet. And once you have this graph, we can apply the same sort of energy based mechanism to say, okay, if you have 2 choices, say that this is one choice A and this is one choice B, you can construct 2 different knowledge graph based interpretations, and each of these will have an energy associated with them. And based on that, we can say, okay, whether this hypothesis has a higher probability of occurrence or whether this hypothesis has a higher probability. And from there, we can label our own data without having ground truth data. So instead of having thousands of labeled multiple choice question answers, we can just answer our own multiple choice or pick our own answers from any choice we have.
Excuse me, sir. May I ask a question?
Yeah, sure.
Sir, how we are distilling this symbolic knowledge? I am not able to get it.
Yeah, so here again, so once the symbolic representation and the contextualization is similarly as what we looked at for the visual data. So these interpretation are these graphs that you come up with. And then since we have energy functions assigned to each of these terms, so this graph will have some probability of occurrence versus this graph, right? So based on that, we can select which label is true, and then from there we can generate this weakly labeled data. So weakly labeled data is basically, we can assign probabilities to each of these choices, right? And since we have that, we can use that as the ground truth to self-train our model. So this knowledge distillation, your student CNLI could be BERT or Roberta or GPT-2 or whatever, right? And we can use pattern theory to train BERT to do this. And that's sort of what happens with our work here. So the PT plus BERT is I was using pattern theory to train BERT, and it does better than just using BERT out of the box without training. Right. So that's the key thing. So we are not training on the data; we're just using it to self-train the model, right?
Okay,
Continuously.
sir. Thank you.
Sure. I think Hima, ma'am, does that answer your question? I think that was your.
Yeah. But coming back to that example where you have frisbee and plate.
Yes.
Yeah, when you have a concept net to have some derived knowledge wherein the object is not seen by the robot so far. But this concept net may not guide you to have a common sense, the answer which has some common sense built into it, right? So how do you counter that?
Yeah, exactly, man. That's a really good question. So that is what we asked ourselves too. So this is our first work that we looked at to use common sense knowledge that's existing to provide these associations. But then we thought, oh no, okay, so if the concept net has knowledge gaps, right? If it is not seeing what we are seeing, then we're not going to be able to get these associations. So what we did in our next work that's under review right now is to use language models to generate these graphs, basically. So to come up with these interpretations if ConceptNet doesn't have this. So we are augmenting ConceptNet with knowledge graphs or with language models to generate more rich interpretations there. And that does way better than what this just pure knowledge based approach does.
Beautiful. But how much is the requirement on the GPU for doing this?
This is completely on CPU, ma'am. Only the neural network is trained on the GPU. So this usually takes around, I think, 1 to 2 seconds per video to run inference.
Okay.
So it's pretty fast, but of course it can be faster, and it has an expensive MCMC step. That is where most time is taken to run. So that is something that we need to look at to make it more practically applicable, and that's one of the reasons why we are looking to retrain deep learning models with this, so that we can reduce the inference overhead.
Can you share this PPTR material related to symbolic knowledge?
Yeah, I can send it to Dr. Rakesh, and I think he can send it to her. Yes. Yeah.
So I think there is one more question, sir, on the chat box. Will multi-actor localization beat object detection?
Oh, I maybe, but we don't know. Our hope is to sort of extend this into action detection. So because right now we assume that every frame has an action, right? So if the action is not there, then but we are still predicting it. It's a false alarm in terms of detection. So Yeah, I think there is potential for us to move this towards action detection, but then it requires a lot more computation changes to the framework to get there. But I think we can get there. Yes.
So one more question. So, sir, can we use this concept to healthcare to predict any disease?
Technically, yes, but we haven't tried it yet. So there are works with probabilistic graphical models. Like if you look at Dr. Daphne Kohler from I think Stanford, she has a company that came out that uses something similar with probabilistic graphical models and Bayesian networks to augment deep learning for it. I think there is potential, but I personally haven't looked at it, so I cannot comment with certainty. But I think it can, and we'll see more and more of these neurosymbolic models come up that will function in the real world. Right?
I think no more questions, sir. So once again, thank you very much, sir, for your wonderful session.
Yeah,
So
thank you for inviting me, Dr. Rakesh. Yeah.
thank you, sir. Thank you.